So here we have a question that relates to the warming or cooling of a body. So basically Newton's modified, Newton's law of cooling. So we know from your theory that it's proportional to the difference between the temperature of the body itself and the surroundings temperature, or the ambient temperature, which they've used T and S to represent them here. The temperature obeys the differential equation dt equals K T times S. And you're told the solution is T equals S plus A e to the KT. A cup of boiling water is 100 degrees Celsius, and a cup of ice water at 0 degrees Celsius are placed simultaneously in a room, which is a temperature of 25 degrees Celsius. After 5 minutes, the temperature of the boiling water has fallen to 55 degrees Celsius. You'd expect that. Boiling water falls in temperature because it's hotter. And the ice water has risen to 15 degrees Celsius. Find the time at which the temperature of the two liquids differ by 10 degrees. So right now, one's 55, one's 15, so they differ by 40. Over time, both will go towards 25. So at some point, they'll differ by 10, and you want to give your answer correct to 2 decimal places. So this is quite similar to a question we did before. So in the sense that we're still doing a very standard sort of modified rates of change, like rate of change question. Last time it was radioactive decay. This time it is Newton's law of cooling. But what may make the question more difficult is instead of giving you one thing, they give you 2 things. So you've got to have 2 things to consider. And then there was some relationship you have to consider. Last time it was to make them the same. This time you need to make them differ by a particular amount. And that maybe the algebra with all the unknowns may be giving you a bit of an issue there. So let's take a look at that. And then once we do that, we just draw the graph. So let's write out what we have. We know that dt equals K times T minus S, where T is the temperature of the object, and S is the ambient temperature. So that means you have 2 objects, right? You have, and you're also told that T equals S plus A e to the KT in general. So those are your general information. But you have 2 things. You have your boiling water cooling down, and you have your ice water warming up. So because your boiling water, I mean, in both cases, your ambient temperature is 25 degrees Celsius. Now, at T equals 0, it's boiling. So your capital T equals 100. And so you really should get into the habit whenever you're doing these questions to read the question and get out all the information you've got. So at T equals 0 here, it was, well, ice water at 0 degrees Celsius. So capital T equals 0 degrees Celsius. Now, you're also told that after 5 minutes, so if we assume T is in minutes, we'll let T be in minutes. So at T equals 5, then this has fallen to 55 degrees Celsius. And at T equals 5, this has risen to 15 degrees Celsius. So this is all the information we have. Now, the question, of course, is basically find T to 2 decimal places such that the 2 temperatures differ. So, I mean, we can have it as T, I mean, we can call it temperature 1 and temperature 2. So we can have this be temperature 1, represented in red, being boiling, this being temperature 2. And so we want to find basically that T1 will always be hotter, right? So basically we want T1 minus T2 to equal, well, you want it to be different by 10 degrees Celsius. So that's what you want to do. You want to find T to 2 decimal places such that T1 minus T2 equals 10. Well, for us to do that, we need to actually find out what T1 and T2 are. So we need to do that, but we recognize that they follow. We recognize that we're told that they follow this law. So we'll use it. So T1 on the left is equal to, well, s plus a e to the kt. So you'll remember, of course, that s is 25. A is, well, not really told, so it's some sort of constant here. I mean, we generally have some idea of what this constant is, but we could easily work it out from the information, as we'll show you very shortly. K we'll have to work out from the information as well. And then T is, well, what you, is just your variable. So S you already know is 25. Now, just as a tip here, A is the difference between the, well, the temperature you started with, in this case 100, and the final temperature, the ambient temperature, which is 25. So basically it will be negative 75, okay? But let's say I don't know that. So we've got T1 equals this at the moment. So let's say I didn't know that. I would formally sub in this. So at T equals 0, capital T equals 100. T1 equals 100. So that means I'm going to get 100 equals 25 plus a e to the kt. So that's 0, which means 100 must equal 25 plus a, give me a equals 75. And then I'm going to use that information to now update my equation. So T1 is now actually equal to 25 plus 75 e to the kt, right? Because that's what we just worked it out to be. So if T1 equals 25 plus 75 e to the kt, now I would formally use my second bit of information over here. I will formally use this now. I will now sub T equals 5, T1 equals 55, meaning 55 equals 25 plus 75 e to the 5k. You'll notice it's all numbers here, except for k. So we will basically be able to solve for k. So take the 25 across, we'll get 30, divide by 75. So basically we'll get 30 over 75 equals e to the 5k. Take the log of both sides. So log of e to the 5k must equal log of 30 over 70, which, by the way, is going to be 6 over 15. Or if you like, it's actually going to be 2 over 5. Right, 6 over 15 is 2 over 5. Log of e to the 5k is just 5k. So k for T1 is just going to be 1/5 log 2 over 5. If you prefer, you can use a calculator to then say that's negative 0.183. And just think about if that makes sense, right? We're saying k is a negative value. T minus s, T is the object, in this case, the boiling water, so it's hotter. So T is hotter than the temperature, so that's positive. We know it should be cooling down, which means dt should be negative. This is positive, so k is negative as expected. So with all of that in mind, we now basically have what T1 is. So let's get rid of all of that and just now update what T1 actually is in terms of numbers. So T1 must equal 25 plus 75 e to the kt. And I'll just write it as kt. I won't write in the number there. I will personally generally use memory for the k, but you can usually substitute. So as the exact value, k must equal 1/5 log 2 over 5, which is approximately negative 0.183. I'll just leave that there. And now we'll do the same thing, except with T2. Okay. So we do the whole thing all over again. We establish what T2 is. So T2 is also going to equal S plus EA e to the KT. For the exact same reason, by subbing the first one, I'll still establish that S equals 25. I'll leave that for you to do. And then we'll establish quite quickly that A will equal, negative 25, right? So in other words, I'm saying T equals T2, being the colder temperature, is going to equal 25 minus 25 e to the KT. All I'm doing is I'm using the fact that S equals 25 and subbing in T equals 0. And if you sub that in, you'll see it works. Okay. Then I need to find my K, which may or may not be the same. They didn't say it's the same, so given they've given us information, we better check it. And it probably isn't the same if they give us the information. So sub T2 equals 15, T equals 5. We're going to get 15 equals 25 minus 25 e to the, 5k. Move that across, you'll get negative 10 equals negative 25 e to the 5k. So e to the 5k must equal 205. So that means, it looks like it's the same. 5k must equal log 2/5. So that means k must equal 1/5 log 2/5. But it's okay because T minus S, in this case, the temperature is lower than S. So T minus S is negative. We expect it to warm, so we expect the rate of change to be positive. But with a negative K, negative 0.183, and negative T minus S, because the temperature of the object is colder than the ambient temperature, so T minus S is negative. Negative times negative is positive. So that means, indeed, in this situation, the K is indeed the same. You can't necessarily assume that, but we have confirmed that. So that does then leave us free to then claim that T2 equals 25 minus 25 e to the KT, where K is the same K. So good. That makes things easier for us, which is good. We don't need to worry about K1 and K2. So where K also equals 1/5 log 2/5, which is equal to negative 0.183. And this is your T2. So at this point in time, you now need to make this happen. You need T1 minus T2 equal 10. So you just take this T1, you minus this T2, and you let it equal 10. So remember, T1 equals 25 plus 75 e to the KT. T2 equals 25 minus 25 e to the KT, where K was equal to 1/5 log 2/5. Just double check we've got everything correct here. 25 plus 75 e to the KT, 25 minus 25 e to the KT, and K is 1/5 log 2/5. And we want this condition. So we make it happen. Right? This is your information. This is the result you want, and we sub it in. You can see the 25 cancel. You've then got 75 so you've got then 75 e to the KT plus 25 e to the KT equals 10. Of course, that gives you 100 e to the KT equals 10. So e to the KT equals 1/10. So that means KT equals log of 1/10. And that means T equals 1/K log 1/10. And this is where you do your calculator. Okay, you remember K is this inexact form. So get your calculator out, type your numbers in, and see what you get. So we're going to get 1 over our K times, and I will use memory for that, times log of 0.1. Give me an answer of 12.56. So we're expecting 12.56 to 2 decimal places. So therefore, after 12.56 minutes, we expect the difference to be 10 degrees Celsius. Now, just as a quick tip, you actually have this button as well on your calculator. So if you press that, then you would have got 12 degrees, 33 minutes, 52.95 this. So if you didn't want it in sort of to decimal places, which is what this question asked for, but if you want it in terms of like minutes and seconds, then this would be 12 minutes and 33 seconds. Okay, like they've already sort of done the calculation for you, right? So that button can be very handy for you. Right? Or 12 minutes and 34 seconds to the nearest second. You don't need to basically do the minus 12 and multiply by 60 and do the conversions for yourself. You can make use of your calculator functions. Okay. So now you are asked to draw a graph of the behavior of the temperature T of both liquids as T becomes large. Well, I mean, we know what's going to happen. They're just going to go towards 25. But I mean, that's basically just asking us to draw graphs. So basically we have to draw graph T1 equals 25 plus 75 e to the kt. T2 equals 25 minus 25 e to the kt. Note that k is negative and is approximately equal to negative 0.183. I mean, we have a very good idea that it's going to go towards 25. So this is at 25. We know that basically it starts at 100. And basically it will just asymptotically go towards that. We know it starts at 0. And we know asymptotically it goes towards that. And that's basically it. That's your graph. And that's how you basically do the question. Make sure you start at 0, make sure you start at 100, make sure you asymptotically follow that through to that asymptote. And that's it. That's how you do the question.